Dear student, welcome to my channel. Topic of this video is classical cryptography. In this video, I am going to explain Hill cipher, one of the substitution method. Now let us start. Classical encryption techniques are opposed to modern cryptography, and their goals is to introduce the basic concept and terminology of encryption and prepare us for studying the modern cryptography. Now in my previous video I have already all the substitution method, only Hill cipher is remaining, and in this video I am going to explain the Hill cipher. Hill cipher substitution method. It is developed by mathematician Lester Hill in 1929. It is a polygraphic substitution cipher because it encrypts block of multiple letters, that is diagram, trigram, etc. at once rather than single letters individually like monoalphabetic cipher. This method relies on some linear algebra and number theory. Unlike simple substitution cipher, Hill cipher encrypts multiple letters simultaneously, making frequency analysis more difficult for the attacker. But it is vulnerable to known plain text attack. If an attacker knows n plain text ciphertext pair, they can solve for the key matrix using a linear algebra. The procedure for Hill cipher. First important is key. The encryption key is an n into n invertible matrix whose inverse is present. That is nothing but key matrix with integer values chosen carefully to ensure the invertibility in modulo 26. Plain text representation. The plain text is divided into n character blocks, which are then converted to numerical vectors using a equal to 0 to z equal to 25. For encryption, the formula is C is equal to K into P mod 26, where K is a key matrix, P is a plain text, and C is a ciphertext vector. For decryption, P is equal to K inverse into ciphertext mod of 26, where K inverse is the modular inverse of the key matrix. Key selection condition, this is very important. The determinant of the key matrix must be non-zero and co-prime to 26 for it to have be inverse in a modulo 26. So all these steps will be clear with the example. Now we'll see a very simple example. So instead of 2 by 2 I have taken instead of 3 by 3 I have taken the example of 2 by 2 so that it is very easy to understand. Now our key matrix is K, which is G, D, P, E. Now we will convert to the particular letter character numbers. So here G is nothing but 6, then D is nothing but 3, B is nothing but 1, and E is nothing but 4. So 6314 is there. Then our plain text is only 4 characters, G double O D. So we will convert. G is nothing but 6, O is nothing but 14, again 14, and D is nothing but 3. So this is nothing but the numerical presentation of the plain text as well as key. Now here the size of the key is 2 by 2. So that's why there is n is equal to 2. So we require to make the chunk of the plain text with the size of n. So we are making the two chunks. One chunk is of 614 and another chunk is of 143, in such a way that each chunk have a length which is equal to 2, because the matrix size is 2 by 2. First we will go for the encryption. Encryption is very easy. In encryption the formula is C is equal to K into P mod of 26. Now this is a K. We make a two chunk because the size is 2 by 2, 614 and 143. Now the 614 and 143. Now first we multiply one. First 6314 into 614, we are getting 7262. We always require our answer to be in mod 26. So after applying the mod 26, we are getting here 0, and when we do 62 mod 26, we are getting the 10 answer. Now for another chunk, it is answer is 9326, again mod 26, we are getting 150. So after concatenation, answer is 0, 10 and 150, and if we convert into the again character value, it is AKPA. So for good we are getting the AKPA as a ciphertext. Now here the matrix inverse must be present, then only we can go for the decryption. So for the decryption step is P is equal to K inverse into C mod of 26. Now we will concentrate on to how to find out the inverse of this matrix in a modular 26. Now our K is 6314. K inverse formula is 1 divided by determinant of K into adjoint of K. Now we will first find out this value, that is determinant. Now determinant for 2 by 2 matrix, for example if matrix is AD, ABCD, determinant is AD minus BC. So AD minus BC. So here determinant is, our matrix is 6 4 24 minus 3, which is equal to 21. Now this 1 by K, determinant K, it is in the denominator. If we take in the numerator side, it becomes inverse. So we are taking this in the upper side or numerator side. Now see, K is equal to 21. See, this K is equal to 21. Now key selection condition. The determinant of the key matrix must be non-zero. Our determinant is 21, which is non-zero and co-prime to 26. And if we see, 21 and 26 are co-prime to each other. Their GCD is 1. So it has an inverse matrix is there. So how to check that? Now first we require to calculate the K inverse, that is the key matrix inverse. Now K into, this is nothing but determinant into determinant inverse, because we have to find out this K. This, when it goes to the numerator, it is like this. So don't confuse between these two. This is determinant sign is given for clarification. So determinant K into K inverse congruent to 1 mod 26, because this condition is there. Our determinant form is 21. We require to find out the determinant of K inverse congruent to 1 mod 26. Now this problem we solve with the extended Euclidean algorithm. Then GCD of 26 21, 26 is equal to 21 into 1 plus 5. 21 will come here, 21 is equal to, and 5 will come here. 5 4s are 20 plus 1, then 5 will come here and 1 will come here. So 1 into 5 plus 0. So in extended Euclidean algorithm we never take this last step. So here 26 minus 21 we arrange, then 20 minus 5 4 1 arrange. I have already published the video on extended Euclidean, so I am not explaining again and again the same thing. Now here we are using the substitution method, that is back propagate. So here we will take first equation, 21 minus 5 into 4 equal to 1. This 4 is coefficient and all rest are the variables. Now we require to put the value for variable. The value of variable here is 5. So we require to put the value of 5. 5 is nothing but 26 minus 21. So when we put and when we solve, we are getting the 5 value. Now check this, we want to find out the K inverse for this 21. So with respect to 21 we get the 5 value. So our K inverse is 5, and when we multiply 21 into 5 and when we take the mod 26 we get the remainder 1. So our answer is correct. So here also we can cross check the answer whether our this value is correct or not. Now only this part is completed now, that is nothing but determinant of K inverse. Now we require to find out the adjoint of K. Now adjoint of K, if matrix is of 2 by 2, adjoint of matrix is this is exchange, and here the negative sign comes. So A B C D, so it becomes DA, and here negative sign comes. Our matrix is 6 3 1 4. Adjoint of K is 4 6 and minus 1 minus 3. Now what we require to do? We require to multiply. Now our K determinant K inverse is 5. So we multiplied this 5 into our adjoint of K. So this is nothing but our K inverse matrix. But we always want our answer in modulo 26. So again we apply the mod 26 here. See, this is our answer. This is determinant K inverse. This is adjoint multiplication, and after that we again apply the mod 26, and after applying the mod 26 we get this answer. Now if we multiply K into K inverse, now this is K and this is K inverse, we are getting this, and when we apply the mod 26 again we are getting 1001. Means what? That when K into K inverse is equal to I, that is identity matrix, means K inverse is present. So this is a condition. So this is not required to solve in exam. It is only to cross check whether we can perform the decryption or not. And here also we are finding out the inverse, in which it is inverse of K determinant, not of the entire of K inverse matrix. Now once we get the K inverse, it is very easy. Now this is the K inverse and this C is 0 10 because our ciphertext is AKPA and its actually values are C 0 10 15 0, then 0 10 15 0. When we multiply and again we require to do the mod 26, we are getting the 6 14, and for the next text we are getting the 14 3. Now 6 4 and 14 3 we again concat. That's why it is called polygraphic technique, because we are taking the data in a chunk. So if our matrix size is 3 by 3, we will take the chunk of 3. When our matrix is 4 by 4, we are take the chunk of 4. So that's why the frequency distribution becomes obscure when we are using the technique in which we are not taking a single character but a set of characters. Now 6 14 and 14 4, and if we use in character, it becomes again good. So encryption and decryption is happen perfectly. So only when this matrix is to be decided before, because this matrix is shared between the sender and receiver. So when this matrix is decided, then at that time it has to be checked that its inverse exists, because not for all matrix inverse exist. Therefore we have to check when we are setting this key as a key matrix, then at that time its inverse must exist, then only you can go for the encryption as well as decryption. So this is all about the Hill cipher technique. So when we want to go for 3 by 3, at that time only all steps are same, only instead of 2 we divide this into the 3. For example, instead of this 2 we make a chunk of 3, and only we require to find out the determinant of 3 by 3 matrix and adjoint of 3 by 3 matrix. The rest procedure is same, but while solving we need some time. So it is very easy to understand with the 2 by 2 example. So this is all about all substitution methods of classical cryptography. Thank you.